Welcome to Experiment 3, Vectors, Physics Lab Mechanics. The purpose of this experiment is to represent force vectors graphically and mathematically, decompose force vectors into components, and find the resultant force vector by both graphical and mathematical methods. The equipment used includes a force table assembly, center post, 3 detachable legs, 3 super pulley clamps, 3 mass hangers, a plastic ring, and a spool of thread. A vector is a quantity that has both magnitude and direction, such as displacement, velocity, and force. The magnitude is shown by the length of the arrow, while the direction is shown by where the arrow points. Graphically, a vector is represented by an arrow, where the arrow length is proportional to the magnitude and the arrowhead indicates direction. Mathematically, a vector can be represented by components along perpendicular axes, usually the x-axis and y-axis. For any force vector, the x component and y component are determined according to its angle, where theta is measured counterclockwise from the positive x-axis, and the signs of the components depend on their directions. To add vectors graphically, the vectors are placed head to tail, and the resultant vector is drawn from the tail of the first vector to the head of the last vector. If the vectors form a closed path, their sum is 0. To add vectors mathematically, all x components are added together and all y components are added together, giving sigma fx and sigma fy, which are used to determine the resultant force, or net force. In the force table setup, strings pass over pulleys with hanging masses, and a plastic ring is placed at the center of the table. The forces acting on the ring are labeled F1, F2, and F3, and all angles are measured counterclockwise from the positive x-axis. The main equilibrium idea is that the third force balances the forces produced by the other two masses, so the ring remains centered and the system is in equilibrium under the action of 3 forces. The experimental procedure begins by hanging 2 different masses over 2 pulleys, adjusting the angle between the 2 strings, then hanging a third mass on the third pulley and changing its mass and angle until the ring is balanced at the center of the force table. After that, the masses are recorded, the magnitudes of the 3 forces are calculated, the angles are measured from the positive x-axis counterclockwise, the 3 force vectors are drawn on graph paper, their components are calculated, the mathematical sum is found, the 3 vectors are added graphically, and the resultant length and direction are measured. The data table records F1, F2, F3, and their sum, including magnitude, angle theta, x component, and y component. The resultant force is calculated from the mathematical sum of the 3 vectors by finding its magnitude and angle, while the graphical method uses a scale to convert the length of the resultant vector into force. The report should include a vector plot with coordinate axes showing magnitudes, angles, and components, as well as a graphing sheet showing the graphical summation of vectors. Finally, the conclusion should explain whether the graphical sum agrees with the mathematical sum, whether the vector sum is consistent with the expected value, what sources of error may have affected the results, how the experiment demonstrates vector quantities, and how the experiment can be improved. This experiment gives students a clear practical understanding of vectors, components, vector addition, resultant force, and equilibrium.